This is a lesson in 1D kinematics in the kinematics unit. Up until this point, we've covered some pretty important information that has built up to this lesson. We went over unit conversion and dimensional analysis in the primer video. We went over definitions and symbolic representations of position, displacement, and distance concepts in the position and displacement lesson. We went over velocity and speed. What's the difference between the vector and the scalar idea of velocity and speed? And all of these, we're getting some equations as well as we move along. Okay, we're building these equations. We also went over the definition of acceleration in the acceleration video. And moving along through there, we've been using vectors, we've been using sketches, we've been drawing graphs, and we've been using multiple representations in order to understand the information and check our answers and set up problems, to set up equations. All of these are important tools to reason with. It's not just the numbers, right? All of these come together, and you can see the graphs over here. We had a position versus time graph and a velocity versus time graph, and getting meaningful information out of there. We've been developing our own equations from word problems. As we enter to this lesson, this won't be as strenuous for this material. As we move forward through the material past kinematics, you'll do this more. But we're still looking at things that we do with word problems. Assign variables, identify knowns and unknowns, etc. And also algebra techniques for setting up equations. We're recognizing the math. Once we get done applying concepts, we have steps of math to move through in algebra and pre-calculus. So all of this is adding up. This lesson is motion under constant acceleration. And developing this idea that if we're accelerating, then there must be a change in velocity. Okay, and of course there's some sort of movement. Let's start with the definition of acceleration. I've given the definition of acceleration, that should say acceleration here. Okay, and that was in a previous video. The acceleration is the change in the velocity over the change in time, and I can write that into more specific more detailed variables. And if I rearrange this equation here, you can note that it's similar to the equation of a line, y equals mx plus b. We get the final velocity is equal to the initial velocity plus whatever velocity was gained or lost due to the acceleration over a period of time. I read that equation like a sentence, and it makes sense to me. Again, we have the b sort of y-intercept, what was the initial value, and then mx, what was the gain according to the acceleration in time. Okay, this time is in elapsed time, so we look at the period over which there was acceleration. And notice again that this is a vector equation. I have the vector notation over these symbols. You need to keep plus and minus signs accounted and assign a coordinate system, right? If we're looking at plus and minus signs, we need to have assigned a coordinate system. I can make this equation a function of time just by noting that it is a function of time, and I can graph this equation. And this will be important as we move forward, maybe intersecting, or I want to know what the equation of the velocity looks like. I can derive the equation and I can graph it. The kinematics equations sort of fall out of all of the definitions of the motion concepts that we've been looking at. We just looked at this one, v final equals v initial plus at. And we can use this in any situation where we recognize that we have constant acceleration. And this will be the majority of questions that would make it to an exam, or if you're looking at national standardized exams or assessments of that type. Can you use these equations for constant acceleration? So this comes from the definition of acceleration. We just rearrange it. The position equation, how an object moves, it's no longer linear. If we just had a constant speed, it would be linear. It would gain the same amount of distance over the same amount of time periods. But what we see when an object is speeding up is that it will gain different amounts of distances because over each time period, it is gaining more speed, and therefore over the next time period, it will be able to go farther than in the time period it did before. What this adds up to is a parabolic shape, and we can recognize that in the equation here for the position versus time. You may recognize, and I'm going to write it backwards, for a parabola, y equals c plus bx plus ax squared. That's the general form. Do you see the t is now analogous to the x variable? And ax squared plus bx plus c, I just rearrange it, and this is the equation of a parabola. So when we're graphing this, we can use this equation as a function of time in order to graph the position of an object experiencing constant acceleration. We'll see this some in this lesson and also as we move forward to free fall motion. Note the form of position with no acceleration. If there's no acceleration, then we lose this final term here, and we recognize this equation is just the equation for constant velocity. Okay, so watch out if you have constant acceleration. I'm going to note that you can have a constant acceleration of 0. 0 is a perfectly fine constant acceleration, but then it has implications for these equations. The velocity doesn't change. The position increases linear rather than by a parabola. Okay. So these are typically given to you on an equation sheet along with these other two. If you manipulate these equations and use a few other concepts, and I'm not going into the derivations of these equations and the motivations of these equations in this lesson. This is more how do you use these equations, and you can access other resources, look in a text, or reference a future video in order to see the derivations of these equations in more detail. So there's 2 more equations here, and what's important that I'm going to note on these equations is that there's a small number of variables. There's a final speed, there's an initial speed with signs because they need a plus or a minus depending on the coordinate system. There's, of course, an acceleration. There's a time variable. And there's some sort of displacement that happened in that time. Notice that there's 5. And when you look at these 4 different equations, each one of them is missing one of these variables, right? So up here, there's no delta x in this equation. Up here, there is no v final in this equation. Up here, there's no acceleration in that equation. There's no time in this equation, right? So when you're looking at solving constant acceleration, you're identifying which variables do you know and which ones do you not know, and what's the most effective equation. Let's practice these ideas and concepts with a problem that you may recognize from a previous lesson, the kinematics lesson on acceleration. We went over this graph and calculated the acceleration for each of the 3 regions on the graph. And notice that I've put the points of the beginning and end for each region. This is a velocity versus time graph. And they're asking us for the motion shown in the graph, write the equation of motion for each region. So they want position as a function of time. Whenever it says equation of motion, that means position as a function of time. So what I'm going to do is give us 3 rows to calculate, to write out the position versus time equation for the 3 different regions. And I'm going to jump in. This equation, I've already put it here for us. And what I'm going to note is that time can be a variable in the equation because I want the position as a function of time. It can stay in there. So I need to figure out x initial, v initial, and acceleration for each of the 3 different regions, which isn't too bad. And so I can say that the position as a function of time for region 1 will be its initial position. And I'm not given initial position here. I'm only given initial velocity, which I'm going to note as 0. And when that happens, I can just assume kind of what I want. And I'm just going to assume that it starts at the position 0. So at 1 second, I have a position of 0. So initial position is 0 plus the initial velocity. Well, I look at the graph for region 1. The initial velocity is 0. I'm going to note that the time is 1, so the time variable in here is going to be t minus 1 to take into account that it starts a little bit later. And then I'll identify the acceleration for the region. I calculated that in a previous lesson. It's 3, so I'll put 3 in here, and then I'll finish out with the t minus 1 to take again into account that 1 second. Okay. There's a couple of zeros in here, and when you end up writing out this equation, you can just omit them, and you would get this one term, 1.5 t minus 1 quantity squared, and that would be the equation of motion for that first period of time. The position of region 2 as a function of time is going to be the initial position, and it's already moved through region 1, so it has some sort of initial position, and I actually know how to calculate it. I just wrote the equation down for how to calculate it. So I'm just going to plug in 4 in here. That's the initial time for region 2. At time 4, I will calculate 1.5 times 4 minus 1 quantity squared. When I run that through the calculator, it is 13.5 meters. So when I think about region 2, its initial position will be 13.5 here. Plus, I need the initial velocity. For region 2, well, the velocity is 9 the whole time, right? At time 4, it's 9. At time 9, it's 9. It's 9 the whole time. So the velocity here, I can put in 9, and I'm going to take into account that this starts at second 4 by subtracting 4 in here. All right, so that's the initial velocity times the elapsed time plus a half at squared, so I'll put a half. I'm going to note the acceleration during this time, and I kind of just said it doesn't change time during acceleration during this time, so that's 0. Again, this term will cross out, and this would be the equation of motion, and you could submit that as the equation of motion. I'm going to calculate, because I've written this out, I'm going to calculate what the final position is when it gets done at that 9 meters per second. At 9 seconds, it is at the final position. So I'm going to put 9 in for t. And when you run this through the calculator, the answer is 58.5 meters. And I can note that I can write these equations. We're going to do this down here in part E, is fill out this graph down here, the position versus time graph. At 4 seconds, we're at, I'm going to broadly draw this in here. This is the point 4, 13.5. And at 9, we're about around 60. I can put that in here. This will be 9, 58.5. I'm not filling in the gaps in between yet. Okay, I'm just filling in these points. I'm going to keep moving along and write out the final region's position as a function of time. Well, its initial position is 58.5. Its initial speed, again, is 9. And I'm starting at 9 seconds. So I'm going to take into account that I'm shifted over 9 seconds by subtracting it here. So I have plus 9, quantity t minus 9. So that's initial velocity times time plus a half at. So I'm going to add on a half. The acceleration during this time period, it slows down. It takes a long time to slow down. So this has a smaller acceleration, negative 0.5. And then I'm going to have the time term here squared. All right, there's a square there. Okay, so attention to detail. Make sure we're keeping track of all this. All right, I'm going to simplify this just a little bit. 58.5 plus 9 t minus 9 minus 0.25 t squared. I simplified those two terms, and that would be a fine equation for the equation of motion. We can plug in the position at 27 seconds. Where is it at 27 seconds? And I know what you may be thinking. Well, Sarah, it stopped, so it's at position 0. But that's not how it works. Like, the object was away and then it started slowing down in that direction. So it kept going that direction and then came to a stop. Okay, so it's still traveling distance in there. And when you plug 27 into this equation, I forgot to put the t minus 9 in here. You would plug that in here, t minus 9 quantity squared. So 58.5 plus 9 times 27 minus 9 minus 0.25, 27 minus 9 squared. When you run that through your calculator, you get 139.5 meters. Okay, so the scale works here. When it gets to 27 meters, we're about at 140. So 27, 139.5. Okay. Now, your natural intuition may be to just connect these dots, okay? But this is not connect the dot class, okay? There's only one region where that's productive here. We have a linear region of position versus time here. There's only one factor of t in here. When I look at that equation, this will be a linear equation, all right? Linear. There's only one factor of t in here. So when I look at region 2, I'm going to note that it just gains position linearly during that time. But when I look at the other two equations here, I have a t squared here and I have a t squared here. Both of those are going to be parabolic in some way. And I'm going to note the sign in front of the t squared term. We're going to have an upward pointing parabola in region 1 and a downward pointing parabola in region 2 because of the difference in sign. Okay? And that makes sense. In region 1, I start out with 0 velocity. Okay? And then as the time moves forward, it can gain more and more speed in a same time period because it was going faster. Okay? So that'll be, you can see how that results in an upward pointing parabola. In the third region, I will have a downward pointing parabola, and that makes sense because it will slowly come to a stop. It won't cover as much distance in those last few seconds, right? So in the beginning, it'll be gaining a lot, but then it will start slowing down. And notice how that results in a downward pointing parabola in some way. I wanted to give you some tips for problem solving in kinematics. We have the equations, but just focusing on the overall strategy. Make sure you're keeping track of interpretation and reading comprehension, attention to detail, and watching for particular words that mean things for numbers, for instance, at rest. This will also concern evaluating your assumptions. Reading your problem carefully will help you understand the problem and not set it up wrong. So watch out for your assumptions. Is it really making sense to what the problem says? Drawing useful sketches and assigning an appropriate coordinate system is key with the kinematics because we're working with vector quantities. We need to keep track of positives and minuses and direction. Okay. Assign meaningful symbols. These symbols are usually in the equations so that in this situation you may need to use a final or which object. Subscripts become more important. You can replace x for y if you're in the vertical direction rather than the horizontal direction. It's perfectly fine to do that. And choose efficient equations, what variables you're going after. Sometimes I see students use 2 or 3 equations where just one would have worked but they didn't notice it. So watch out what your knowns and unknowns are and how they match up to your equations. And finally, check your answer. Right? Once you solve algebraically and plug in your numbers and kind of get your answer, that's not the end. Make sure you're evaluating your answer for units and also that it makes sense in the context of your problem. On a larger level, I wanted to touch on problem solving as well, and I had gone over this in the primer for formalized reasoning and problem solving. Was what is the process you're thinking about? Are you aware of how you're solving problems as you're solving problems, or are you just fumbling through them? You should become sharper in solving problems, in monitoring where and how far you are in solving a problem. Initially, you would start out like, what are the relative concepts? When we're solving problems like in this lesson, you already know that it's 1D kinematics. But on an exam or other assessment, what are the relevant concepts? How do I know they apply? So we'll be watching out for cues on how do I know that this is this concept or this equation. Do I have a clear overall strategy? Sometimes you can see the strategy, how many steps out, or sometimes like you only are able to get it started and then not like have an idea after that, and that's fine. Sometimes that's what happens. A lot of times that's what happens when we solve problems. You may just simply move forward one step with what you know and then figure out what to do after that, and that's a fine way to solve it. In which part of the problem solving strategy are you? What is the next step? What did you do that worked? Because as you monitor your problem solving, if something happens that did work, you can keep note of that. And if there's something that happened that didn't work, you can say, I'm not going to do that again. Or what about this problem that this didn't work in this particular problem? Always, does my answer make sense? How does it make sense in the grand scheme of things? And also, how does this problem differ from the other problems? Many times problems will switch the focus or the aspect, the angle of the concept. So instead of focusing on acceleration, they'd focus on the final velocity. And you may need to use equations in different direction or combinations of equations. And so, but there's a small number of equations, right? And so you should, as you're doing this, become more and more familiar. And again, that may help you with your problem solving strategy when you get more and more familiar and keener about what emphasis is in this problem. Then that can bring up a strategy for you sooner. So I have a word problem. The first word problem that I have for you is the accelerating car. Typical, straightforward. I'm going to just accelerate a car from rest. A driver of a car accelerates from rest at a rate of 9.5 meters per second squared. That's an acceleration, right? Meters per second squared, and I can write that here, identify an unknown, for a distance of 450 meters. And I'm going to note that that's the displacement, okay? It seems to me, and you can draw a picture for this. This is something that you could do. There's an initial position. There's a final position. X initial is 0. X final is 450 meters. We start out. It starts from rest. So that means V initial equals 0. I don't know V final. It doesn't tell me V final. And I also don't know the time. I don't know what the time is. But I do know the acceleration throughout the whole time is in the same direction of the displacement in 9.5 meters per second squared. I'm going to note here, before I get too far, and assign a coordinate system just to be explicit. It may seem too easy in this situation. Why would you need a coordinate system? But it's a habit of mine to develop, so I'm going to keep developing that. Okay, it says determine the elapsed time. Okay, so I already knew that was an unknown. Determine the elapsed time for this motion. Verify your answer with a position versus time graph. Okay, determine the elapsed time. So when I look at the information given, I know the acceleration, I know the position, and I know the initial speed. So I look through these equations. It's sort of like plug and chug and equation hunting. But or I may also note, it may be easier to go backwards. I don't know the final velocity, so I want an equation that does not have the final velocity in it. Well, it's not that one, it's not that one, and it's not that one. So I must be left with this. This will be the equation that I'll use in order to solve for the time And so let's plug in what we know. X final, we know, is the plus 450. X initial was 0. Plus V initial t, well, that's plus 0t. Remember, the initial speed is 0. T, I don't know. Plus 1/2 times the acceleration. I know that, 9.5 t squared. I get the equation set up. This term is 0. I can eliminate it, right? It's just kind of sitting there, and I can eliminate it. So I'm going to note that 450 equals half of 9.5. Well, that's 4.75. I can divide that by 2. T squared. So I can divide by 4.75 on both sides. 450 divided by 4.75, and take the square root on both sides, and that would give me the time itself. T equals the square root of t squared. When you run this through your calculator, you get t equals 9.7368. And the units is time seconds. Okay, so there's the time. We could reduce this to two significant figures, maybe 9.74 seconds to have a final answer. 9.7 seconds. That's two significant figures would be a final answer. Okay. I'm going to keep a hold of this equation. I'm going to note that the position versus time equation will be 0 plus 0 plus 1/2, 9.5 t squared, and I can graph it then. That will allow me to graph a position versus time graph. Okay, so I will pull up the graph here, and I'm just going to plug this in. I'm going to use x and y variables, 4.75 x quantity squared, and that's fine. I'm going to limit this domain. We started at t equals 0, x 0 less than x, and I'm going to limit it to 10 seconds because it seems like it doesn't go farther than 10 seconds, but that's fine. Okay, so let me adjust the graph here. We'll get this, we can view it, and I'm going to extend the axes a little bit. I'm going to zoom in, and this is zooming in on Desmos. You just adjust the scale for each. On a calculator, this would be the zoom function. You can rescale the picture. So let's see, it says 9 seconds. So let's go to 10. Okay. And I need to adjust the y-axis. It goes much farther than 14.52. It goes 450. So maybe let's go to 500. Okay, what do we got here? All right, look at that. I have a graph. Okay, there's the graph. It says at 10 seconds, it doesn't know where it is. But notice that I can see where it is. That's the graph. So we expect it to be an upward pointing parabola. It has a positive slope, and it's squared. I'm going to put in here y equals 450 because we want to know at what time does it reach 450. So y equals 450. So that's where it's gone, 450 meters. And now we have 9.733. That's what I had, 9.7 seconds. It reaches 450. So that's how you can verify your answer with a graph. You will need to show your answer algebraically. You will need to show this work, but you can verify your answer with a graph. The next part says calculate the car's final speed. Okay. Well, there's a couple of equations with the final speed in it. And I have time, and I have initial velocity, and I have the acceleration, and I have the distance. Seems like a lot of these work. Let's see. V final. I'll take the easiest one, it looks like. V final equals V initial plus AT. The initial velocity was 0. The acceleration was 9.5. The time was 9.7368 I got. Super easy. Plug that through. When you plug that through, you get 92.46621 meters per second. That's right. Something over 9.5 times something over 9.5. It'll be less than 100, which is 10 times 10. So that makes sense to me. Okay. You could use any other equation up here with V final and solve for it and get the same thing. I was kind of interested, 92 meters per second, how fast is that? When you do a conversion on this or plug it into a calculator, you actually get 206.9 miles per hour, which is actually a pretty interesting car. Speed up to 206.9 miles per hour in less than 10 seconds. That's one heck of a car. So I'm impressed with this accelerating car. The next problem I have to illustrate the kinematics equations is the bike crash problem. Two children are riding bicycles and they're on a head-on collision with each other. Oh no. Oh no. Oh gosh. They both try to slow down, but their crash is inevitable. They're two kids. I can see this happening. The first child slows down from initial speed of 1.9 meters per second at a rate of 0.2 meters per second squared. The second child slows down from the initial speed of 2.3 meters per second at a rate of 0.2 meters. Okay, so they're decelerating at the same rate, but they have two different initial speeds. If they begin 12 meters apart, determine where they meet and verify your answer with a graph. Okay, interesting. Determine where they meet and verify with a graph. So when two things are meeting, the strategy, and you may remember this from previous problems, the strategy is to say that they're at the same place. Right? They're meeting. They're at the same place. So if they're at the same place, what this is going to suggest is that we need the equation of motion for position, right? For position. And I'm going to get a picture going just to make sure that I kind of encoding this and making sure it looks right. They start 12 meters apart. I'm going to put the first child over here at x equals 0. The second child starts 12 meters away, so that's x equals 12 meters. And this will be child 1, child 2. The initial child has a speed of 1.9 meters per second. That'll be v initial 1. The second child is moving in the other direction, right? This is a vector. And it has a larger velocity, 2.3 meters per second, and that will be v initial, comma 2. And notice how I'm using the subscripts to really designate which child and what the information corresponds to. I'm also going to write in here, and I can use a little bit different color vector. They both have an acceleration. This one's acceleration, remember, is going against the motion, right? They're both slowing down, and I have to take that into account. It's pointing in that direction at 0.2 meters per second squared, and the other one is also slowing down at 0.2 meters per second squared. Okay, they're pointing in opposite directions, and I can label those two. A1 equals that, and A2 equals that. Two different accelerations. We'll proceed to write out their positions, their equations of motion, x initial plus v initial t plus 1/2 at squared. We'll fill that information in for these two different children. So the position of child 1 as a function of time, that child starts at the initial position 0. It is moving, that child is moving at 1.9 meters per second, t. And then its acceleration is in the negative direction, right? In the negative direction. Negative 0.2. And then I'm just going to tack on the t squared. It's as a function of time. I can do the same thing with the other child. The other child starts at 12. is moving in the negative direction at 2.3. And I didn't assign that over here. I'll do that over here real quick. This is the positive direction. The second child is moving originally in the negative direction. And when I look at the second child's acceleration, it is pointing in the positive direction. And I'm okay with that. For it to be decelerating and have a positive sign, that just means that these two vectors are pointing opposite one another. As long as the sign in front of the acceleration is opposite to the sign in front of the speed, I'm going to have deceleration. Same thing here. These two signs are opposing one another. That's his slowing down. And now that I've derived the equation for both of these children, I can proceed to apply what I know, that when they meet at meeting, right? At meeting, the position of the first child, whatever their equation is, will equal, they're at the same place, the position of the other child. And that will be my strategy to solve for the time, is to set those two equal to one another. It seems like too we're going to get a quadratic. I'm okay with that. And so let's write this out. I have 1.9t minus, I'm going to simplify a little bit, 0.1 t squared equals 12 minus 2.3t plus 0.1 t squared. I'll put a 0.1 in there so that it doesn't look so weird. 0.1 t squared. Okay, definitely a quadratic. I'm going to move these terms over to the other side and get 0 on one side, everything else on the other. Negative 2.3 plus a negative 1.9 will be a 4.2t. And then these two will add together as well. T squared. You can check that with your algebra. So we have a quadratic to solve. You can run this through your favorite quadratic equation solver. You should get two equations. That makes sense, right? If I have a parabola intersecting with another parabola, they should intersect theoretically in two different points. It turns out when you solve through for this problem, the first time is 17.5 something or so, and I'll put a second here. And the other time is 3.4 seconds. So we have two times. Let's look at the graph, right? Because both of these times seem like they could, right? Like they're both positive. So they could both happen. There's a small time and then there is a large time. And that's kind of curious to me, okay? So let's graph these two equations. We can graph this. Let's go over to the graph. Let's see what's going on the graph. So the first equation, y equals 1.9 x minus 0.1 x squared. Okay, and when I look at this, I see increasing distance, and then slowing down. Okay, so it doesn't travel as far in the same time period. So this is slowing down. Okay. It's a pointing down parabola. I'm fine with that. Let's draw the other one in here. Y equals 12 minus 2.3x plus 0.1x squared. Okay, just as I expected. Two intersecting parabolas. And I'm going to note the two places they cross, and I'm going to note that these are the times that I calculated. 17.8 or 17.6 and 3.41. Both of those were the answers I got calculating in my calculator. Okay. Let's think about children. Like, which answer do we want here? Well, one child started at 12 and the other one started at 0, and they're heading towards each other, and they were on a head-on crash. So it seems like this is the point where they crashed. What happens with the rest of the graph is if they had missed each other and kept decelerating, they would eventually turn around and then run back past each other on a second trip. That's what this second point is. And I don't care about that second point. That's not what we care about for the problem. We only care about this initial meeting when they actually do crash. We verified our answer with a graph. I can go back to the slide. So we do not want to retain the large time here. We will cross it out and say that this is our answer. This is the time at which they meet. It says determine where they meet. Okay, so where is a place? I have the time, and what I'm going to note is I have the position of both of them. If I plug the time into either one of these, that will tell me the position at that time. So if I say x1 of 3.41 equals 1.9 times 3.41 minus 0.1 times 3.41 squared, you can calculate that. When you run that through your calculator, you get 5.317749 meters. With one or two significant figures, we're looking at 5.3, which makes sense when I look at it. When I look at this and think about it, right, reflecting on my answer, they meet at 5.3 meters, which is less than halfway at 5.3 meters. So I'll put that in here. Maybe this is 5.3 meters. This is where they meet. And the other one is a little less than 7, right? 6.7 meters this way, 5.3 meters this way. They have to add up to 12. And it makes sense to me because the initial child was going slower to begin with. So the other child's going to travel more distance as it slows down, and they meet closer to this first child. So I'm okay with that.